Okay, so I'm going to go through some more integration techniques, which may or may not include inverse trig integrals, but from your textbook, page 523, and I'll make a copy of this for everybody. You have your rules, okay? I'll put these things together, what your basic integral rules were. Well, sometimes integrals don't fit those general forms. We have to get them there. That's why we needed that's the need for use substitution. So here's some techniques that if you saw this particular expression in an integrand, maybe you have to do something to it before you can attempt to fit it to a rule. Expanding, we square binomials, we're very good with that. Separating the numerator, okay, and we'll look at one of those today. But if you look at this note, we know we can't break up a denominator. We can always split up a numerator as long as it keeps the common denominator. Completing the square, I'll do a couple examples of that today. Dividing improper rational functions. So when the degree of the numerator is greater than or equal to the degree of the denominator. That would be a useful tool. Adding and subtracting terms in the numerator. I'll do one of these today. Okay, I needed to add 2 to get this to work. Well, I can add 2 as long as I maintain balance by subtracting that 2 as well. And we do that. That's exactly what a use substitution is. We introduce numbers all the time as long as we keep balance on the integral. Trig identities. Okay, all coming back to our Pythagorean identity there. And then multiplying and dividing by Pythagorean conjugates. Okay, so I won't be able to do an example of every one of these today, but you will be practicing them in class. Alright, so the antiderivative of sine x divided by 7 plus cosine squared x dx. Looks like it should fit arctan. We have something being squared in the bottom. There's no square roots. Finally, we're seeing an a that is not a rational number, so it does not need to be. U will be square root of cosine squared x, which would be cosine of x. The derivative of that is negative sine x dx. Okay, so that sets itself up nicely for us. We put our negative out front, balance the integral with a negative, 2 negatives. So now we have du divided by a squared plus u squared. So that is our arctan. So the negative from the front of the integral, 1 over a arctan of u over a plus c. You do not need to rationalize these denominators. Okay, so you leave it like this, you would get full credit. Okay, negative 2 to 2, 1 over x squared plus 4x plus 13. Okay, the form that it's in now, maybe it would, what we want to fit it to is arctan. It can't be arcsine, can't be arccosine. Okay, I look at a u substitution. du is 2x plus 4. There's no other x's in the integral, so none of that is going to work. So this is an example of completing the square. Let's fit it in the form that we need it. All right, so completing the square. X squared plus 4x plus something. And then whatever I add here, I'm going to have to subtract from 13. All about keeping balance. Half of 4 is 2. 2 squared is 4. So then I'm going to have to subtract 4 there as well. Completing the square. X plus 2 quantity squared plus 9. Now look at what we have down here. So negative 2 to 2, 1 over 9 plus x plus 2 squared. A is 3, u is x plus 2, and du is just dx. So once we complete the square, it fits perfectly into our arctan. So I have 1 over a arctan of x plus 2 over 3. evaluate it from -2 to 2. Take a minute. Evaluate this answer for me. Okay? Plug in the upper bound, subtract the answer you get when you plug in the lower bound, and this is non-calculator, so your answer will be in terms of the arctangent function. Three all over 2 square root of x, 1 plus x dx. Okay, so a couple things we can do here. If you think to distribute the square root of x, then we would get 3 over 2 x to the 1/2 plus x to the 1, 2, 3/2. Sorry about that. All right, adding exponents, 1 plus 1/2. Well, this doesn't help us at all because we can't ever split up a denominator. So that method not likely to work. If we pick u, if we're going to pick a u substitution, let's start with square root of x. All right, I don't know if it's going to fit into an inverse trig integral. It looks like maybe it could be arc secant, but then we only have the square with the one thing with the square root. We have no variable in front of that. So let's work with a u substitution. All right, so I get 1/2 x to the -1/2 dx. So 1 over 2 root x dx. Okay, so 2 root x du is going to be my substitution for dx. Now when I look at this, all right, I got all sorts of things going on. So let's start replacing. I have 3/2 square root of x, 1 plus x, and the only thing I have right now is that I'm going to replace dx with 2 root x du. All right, from here I get my square root of x to cancel. I get my 2's to cancel when I bring that out front. But I still have this in terms of x. When I need to make a u substitution, I have to get rid of all of that. So look at what we started with. If u is equal to square root of x, then u squared is equal to x. So now I have x in terms of u. So if I make that replacement, now my integrand is the arctan function. So a will be equal to 1. So the antiderivative, 3 arctan of u, and we pick u to be square root of x plus c. So you have all these rules to use. You have to manipulate the integrand so that we can get it into one of those possible rules. One to 4, 1 over x square root of 16x squared minus 5. All right, looking at this one, we have to fit it into arc secant because square root of u squared minus a squared. We have the square root. The form is correct. The function in terms of x minus the real number. We have that u next to the radical. So now let's get it to fit the form. A will be square root of 5. U will be 4x. So du is 4 dx. Put my dx in here. So du divided by 4 will be dx. Okay, so then if I'm going to replace dx with du over 4. And in order to use this rule, these u's have to be the same. So we said u was equal to 4x. Well, then I need this next to the radical to be a 4x. So to maintain balance there, I'm going to then multiply that by 4 as well. So now when I go through and make my u substitution, I have 4 over u times the square root of u squared minus a squared. And now let's bring this 1/4 out front. All right, that was from the u substitution. So now I have the antiderivative u squared minus a squared du. Now it fits the form of our arcsecant integral. So 1 over a arcsecant of u over a, absolute value of u over a. And I'm integrating that from 1 to 4. Again, we don't need to rationalize. So plugging 4 in, arcsecant of 16 over the square root of 5 minus arcsecant of 4 over the square root of 5. It's ugly, but it's your answer. Now from here, just to go back real quickly, notice that the 4's ended up canceling each other out. If your u substitution was not dividing by 4, you would still need to introduce this number to make u match the u that you picked here. So like I said to start, we can introduce numbers at will, and then they just cancel each other out. I kept that in there just to show you that just in case this wouldn't be the same, we would still keep it in the antiderivative. Okay. Let's do this one. This one's a little lengthy. All right, antiderivative of 2x minus 5 divided by x squared plus 2x plus 2 dx. Okay, let's try u substitution. If we pick the denominator, the derivative of u is 2x plus 2. We have the 2x, but we don't have the plus 2. Okay, let's try to break up the integral. Minus 5 over x squared plus 2x plus 2. Okay, I'm allowed to separate the numerator as long as I keep the common denominator. So now let's go back to the u substitution here. I still pick my denominator. But now in order to keep this, in order to get that plus 2, I can add 2 to this expression as long as I subtract, let me add 2 here, because really I'm subtracting 2 if I go back and distribute that negative. Oopsie. Okay, so let's look at this again. I have 2x plus 2. I'll keep it over u. So now I have negative 5 here. Okay. I added 2 to this integrand, so I have to subtract 2 from that integrand. Okay. It's a plus 2 here because I didn't just think about distributing that negative. So if we keep the integrals as plus the other numerator, if I kept that negative sign in there, now I'm adding a negative, and adding a negative we know is the same as subtracting. Up here, I was subtracting a positive, so that's how I still kept the balance of the equation, or the expression rather. So using my u substitution here, 2x plus 2 is du. So that, we know that antiderivative rule. Natural log of u, x squared plus 2x plus 2 plus, now let's work on this. Okay, no more use substitutions because I don't have any x's in the numerator.